Hi everyone, welcome to lesson 13.2, integrals of vector functions and projectile motion. So we're going to dive into integrals for the first time now, and if you are a student who's enrolled in BC Calculus concurrently with this course, we should not be exceeding what you've learned already timing-wise. So this is actually, in today's lesson, very basic antiderivatives. But we'll progress through to more advanced ones in Chapter 15. So integration in Chapter 13 won't be terribly involved. Alrighty, so let's move on. So we're going to talk about indefinite integrals and how you deal with the plus c part over here in the formula for an indefinite integral. You know, you're stuck with the plus c in your answer unless you've been given an initial value. Turn it into an initial value problem. And so we're going to dive in here and just demonstrate to you what this is, because the I, J, and K parts are not variables. They're very specific indicators of standard unit vectors, so they just kind of go along for the ride when you do integration. And so the idea here is that you are going to be integrating one component at a time. Adjust the tilt of my tablet here. Cosine of t dt, and that's kind of your I component, okay? Because the answer to the integration of a vector valued function is also going to be a vector valued function, okay? So then we'll have integration of j dt. Oh, actually, I've been putting the components. You could put it inside the integral. It's fine, but it's more confusing. So integral of dt in the j direction, and then plus the integral of negative 2t dt in the k direction. That's what we're essentially doing, okay? So the antiderivative of the cosine of t is the sine of t. Okay, and that's in the j direction. It's supposed to be a parenthesis. J. I just have to write a little bit slower to make this a little bit more readable. And then the integral of dt is just t, and that's going to be, this is supposed to be I. Pardon me. I've been making that mistake all day. I don't know why. I said I, but I wrote j. This is in the j direction. And then the integral of negative 2t dt, well, that's going to be minus 2t squared over 2, right? So we really don't need the 2 over 2. So let's just neaten that up a little bit. So we're going to end up with t squared k. And then we'll say plus c. And we'll make it a vector by putting a bar over it, since this is a vector. So we don't know what the constant vector is that might be there, so we'll just put it at the end. And that's the answer to our question. You know, you don't have to put the parentheses around sign here if you're neat enough. So this is a very basic treatment of integration where we look at one component at a time. Okay, so definite integrals have, if you're going to take the definite integral of a function r of t that's a vector valued function, then you're just going to do a separate integration on each component and evaluate it from a to b. Okay, so if you'll recall, the fundamental theorem in calculus has you performing the integration and then the function value of the top limit minus the function, or the antiderivative value of the bottom function is going to be your antiderivative. Okay, so in this way we get rid of the constant vector that's unknown, and we have a particular vector for an exact answer when we evaluate it. So this is, if you'll recall, the fundamental theorem of calculus, okay, which by the time you got to it, you would think the fundamental theorem of calculus, so exciting. It really is not that big a deal. Nor is the fundamental theorem of algebra, nor is the fundamental theorem of arithmetic. None of them are super surprising things, but they're all very pivotal in the progress of mathematics and the consistency. So here we go. We just did this integration, and now we're going to evaluate it from 0 to pi. So this ends up being the sine of t, okay? And some teachers use parentheses, some teachers use brackets. I don't care which one you use as long as you put the limits on it, okay? And then we have t from 0 to pi. So I am just evaluating my findings on example 1 from 0 to pi. So I'm writing out here what I'm planning on doing. And all of these still have I, j, and k in them. Because the answer is still a vector, and when you leave these out, you are actually wrong, okay? So evaluating this, the sine of pi minus the sine of 0 as the I component. All right, and this would be subbing in pi for t, pi minus 0, j. And then negative 2 pi minus negative 2 times 0, and that's our k component. And so the sine of pi this is 0 minus 0, so there's no I component. Pi minus 0 is pi j, and negative 2 pi minus 0. Oh, you know, I wrote that wrong. That was supposed to, I didn't put the integration part in. This is supposed to be t squared. So this will be pi squared minus 0. So this will end up being, and it's negative. Sorry, caught my own error though. That's always good to catch your error. Negative pi squared k. All right. One would hope that you could catch your own errors every time. So here is a vector with no unknowns. So this is not a variable. We don't need a plus c at the end of it. This is an actual known vector with constant values. I know good and well that you know pi is a constant, but everyone slips up once in a while and thinks of it as a variable. Okay? All right. So now we're looking at the path of a hang glider, and you're not normally given a picture of the vector valued function, but I want you to realize, like it says in the comments on the figure, this is not a helix, and I'm wondering if anybody knows why it's not a helix. It certainly is a spiral path, but a helix has a constant rate of increase, and this has an exponential rate of increase in the height of the function, so that's why it's not a helix. However, if you look at the acceleration function in the question, that one is a helix because the rate of increase of the vertical component is just 2 instead of something like t squared. All right. So suppose we do not know the path of a hang glider, but only its acceleration vector a of t. And here we have all of the components. We also know that initially at time 0, and usually they'll say initially and they won't bother saying at time 0. So I want you to realize that the beginning, the initial point when we start counting time equals 0, is implied when they use the word initially. All right, the glider departed from the point 400 with a velocity v at time 0 equals 3j. So find the glider's position as a function of t. So we know that we're going to have to integrate acceleration to get, okay, if you center acceleration, you get velocity, right? And if you integrate velocity, you get position, which we call r, all right? Now, I could write this with all manner of different symbols, but this is the general idea. So we're going to integrate a of t dt, negative 3 cosine t. I'm going to do dt, and then I'm going to put I right here, okay? And then minus the integration of 3 sine of t dt, and that's j, and then plus the integration of 2 dt, and that's times k. All right. So performing this, and I could have put the minus 3 out front. Okay, it winds out front here. And the antiderivative of cosine is sine of t. Okay, and that's still in the I direction. So we've got v of t, and then we've got minus 3, and the antiderivative of sine is negative cosine, so negative cosine of t in the j direction. And just make sure I'm doing this right, checking my notes every once in a while. And then the antiderivative of 2 is 2t, and that's in the k direction. Now, we do have to put, because this is an indefinite integral, some unknown constant vector that we don't know what it is. But we've been told that the velocity at time 0 is 3j. So if we substitute in 0 for t, we should get 3j. So putting in 0 for t here, sine of 0 is 0, so the I component is gone. Putting in a 0 for t here, cosine of 0 is 1 times 3 is 3j. Okay, and then putting in a 0 here, 0 times 2 is 0k, and then we bring down the plus c1. So subtracting 3j from both sides, 0 is the vector c1, which makes 0 a vector. So now we know we don't need the constant term on our velocity vector. We do actually have a legitimate vector valued function to describe velocity right here. Okay. We can't stop here though. We've been asked to find the position as a function of t, and I want you to realize that we do have an initial value. This right here, the glider departed from this point. Okay, so we'll deal with that to help us get rid of the constant value when we integrate v of t. Okay, so v of t, integration of v of t dt, so we'll do it like this. V of t dt is what we're about to do. So we've got to integrate this right here. So I'm going to do this in something you can see on top of the blue, I guess, here. All right, so the integral of negative 3 sine t dt I, and then the integral of 3 cosine t dt j, and then the integral of 2t k, 2t dt, excuse me. 2t dt. Please be thorough in how you write expressions. Some people leave off their dt's and it's wrong. So don't leave those off. But then we also have some unknown, I'm going to say C2, some unknown constant vector that we don't know. So if this is our position function, all right, and our position function at time 0 is 4i plus 0j plus 0k, then we know that if we substitute in a 0 for t, we should get 4i. Okay, so let's do that. Let's do that in red. Okay, so 4i equals, and if I substitute a 0 in for t here, sine of 0 is 0. Oh, actually, I didn't do the integration yet. That would help. Jumped ahead in my notes. Okay, so negative 3, the antiderivative of sine is negative cosine t. There's my I component. All right. 3, the antiderivative of cosine is sine j. And the antiderivative of 2t is, you want to say t squared over 2, and the 2's cancel, so you got t squared k plus c2. Now, okay, that is our r of t. Now we can do the substitution. Okay, r of 0, which equals 4i, and then we substitute in 0 up here. So 0 in for cosine of t is cosine of 0 is 1 times 3 is 3i. The I components don't match. Sine of 0 is 0 times 3, so the j component is 0. 0 in for t squared is 0k, so that component isn't in there. And this is plus the vector C2. And then when I subtract 3i from both sides, I get that I is our vector. And we can come up with our final answer that the glider's position as a function of t, r of t, make sure you indicate that it's a vector, is going to be here with our constant vector added in. Our constant vector is I, so I'm going to write our first component, I like to see that as a parenthesis, 1 plus 3 cosine ti. All right, so that's C2 plugged in here, but realizing that C2 is an I component, just one I went ahead and combined it with my I vector. Then the rest I just copy, I combine the one with this. So 3 sine t is our j component, and down here t squared k is our k component. So there, after doing integration twice, is our position vector as a function of t. All right, so we need to look at ideal projectile motion. So I'm going to kind of summarize briefly what the book says. It's really, really good if you go through this and read it closely and understand it. It's very similar to what you did in single variable calculus, and since these are all functions of a single parameter, it's not vastly different. It's just taking integration in vector form or vector functions. So when we do ideal projectile motion, we make some assumptions, and this is from page 761. We are going to assume that the projectile at time 0 is sitting at the origin. Okay, so that's what this says. The position is the 0 vector at time equals 0. Okay, and so this is an equation that we get from a vector unit in a pre-calculus class. So the magnitude of v naught is the speed, the initial velocity as this projectile begins its motion at time equals 0. The speed is this red vector v naught here, and the magnitude symbol here means we could just write it as a non-vector expression. Just plain v sub 0 is the initial velocity expressed as a scalar number, and then we multiply it by the cosine of alpha. So alpha is the angle that v naught makes with the x-axis, and v naught times the cosine of alpha would be the distance that the projectile is moved by the horizontal motion. Okay, the force of that velocity in the horizontal direction will give us the horizontal component of the vector, and this is how we do it without using the extra symbols for speed. And here the sine of alpha times the initial speed gives us the vertical component of the motion of the projectile. All right, so this is a formula we used in analysis, pre-calculus, whatever class you took. And then the initial vector, initial position vector, is just 0. Okay, now we all remember force equals mass times acceleration from physics class, and so we're putting in the second derivative of position as the acceleration. And if we're looking at this, really the only force that is acting on this projectile as it is moving along the parabolic trajectory is gravity. Okay, so once the ball is in motion, or the projectile, or whatever it is, bullet, rocket, whatever you want to think about is flying through the air, it is being, we're assuming that the only force acting on it is the force due to gravity. So we need to be able to do this in the metric system or in the British system, so I'll give you those numbers in a moment. But we realize that this assumption is something we have to do to simplify this process. We know that unless we're operating in a vacuum, we've got all kinds of friction, we've got the force of the wind, we've got any number of things, the fact that gravity isn't technically a constant based on altitude. There's all kinds of things that we have to kind of throw out the window that are real in order to have a good theoretical foundation for this mathematics. Okay, we cannot start with all of the realities of actually tracking a projectile through atmosphere of the Earth, okay? So we're assuming a bunch of things, but right now we're assuming that the acceleration due to gravity is the only physical force acting on the projectile as it's moving through the path. So if that is the case, our force, our mass times acceleration here, is going to be downward in the J component. So negative is where that comes from because it's moving down toward the Earth. The mass times G, the acceleration due to gravity. And so we can divide both sides by the mass and come up with a second derivative of the position function is negative G in the J direction. Okay, so that'll become a part of our derivation. We've got our differential equation. We're going to do an initial value problem here with our differential equation here with initial conditions that the position at time 0 is just going to be a symbol r naught. The velocity at time 0 is just going to be dr dt. Thank you, kitties. I'm throwing my stuff on the floor. And all of this is when time equals 0. So this is the setup of a typical initial value problem. All right. So we're going to integrate this expression right here, okay, and we have to put our dt's in so that we can be proper. Please don't leave those out. I'll say that 1,000 times because I don't want you to leave them out. So the antiderivative of d2r with respect to t twice, all right, is dr dt. And the antiderivative of negative gj is negative gt, okay? And we are disregarding the constant here in this derivation, all right? Actually, we're not totally disregarding it because there was some initial velocity in there that we don't know, okay? But that's what we're using here for our initial condition. So we know it was at time 0, it was v naught, so we can just go ahead and put it in as our vector v naught, all right? Now, we want r, so we've got to integrate again. So put in our dt here. All right, and here's what we've got. The antiderivative of dr dt is r, and we're going to have negative 1/2 g, excuse me, t squared. G is a constant, so that it's basically the antiderivative of t is negative 1/2 t squared. The negative is from here. And then we've got plus v naught t plus some acceleration vector, or excuse me, some initial position. So whatever the initial position was, r instead of a rather. So this is a formula for our initial position that we can use to help us solve these initial value problems. Now, if we go in and substitute from here, okay, this is v naught, and we're going to substitute those values in for v naught here, okay, and also our initial value of r naught was the vector 0, right? We have some substitutions we can do here, and we're going to wind up with, here we go, let's just delete this. Once we substitute in our values for v naught, we're going to wind up with these components and here, and then our r naught is just plus 0, so that doesn't change anything. We have an equation for ideal projectile motion. And then if we want to write this in the parametric form, we simply drop the vector notation, the I and the j, and separate them into two equations, x equals and y equals. So these are handy forms for solving the problems in this section, and we're going to look at example 4 here and see how this looks in action. Okay. By the way, the parametric form, this equation would give you the distance downrange from the initial launch position, and this would give you the height, and both as a function of time. All right, so example 4, it says, a projectile is fired from the origin over horizontal ground, so we don't have to worry about hills and such, at an initial speed of 500 meters per second. Okay, so meters per second, we're in the metric system, in which the acceleration due to gravity is negative 9.8. By the way, if we were in the British system, the acceleration due to gravity would be negative 32 feet per second squared. So make sure you adjust your g value depending on what system you're doing it in. This would be meters per second squared. Okay. So over here, initial speed, that is going to be v naught is 500 meters per second. Our launch angle alpha is 60 degrees. Not that you can't do this in radians, but it's traditionally done in degrees. We want to find where will the projectile be 10 seconds after it's launched. Okay, so t is 10 seconds, and g will be over here in the metric system. All right, so we're going to fill in. We've got our R equation, v naught cosine of alpha t times I, and then we've got v naught sine of alpha times t minus 1/2 gt squared, and that's our vertical component. Now, substituting all the values we have, we're going to have 500, and the cosine of 60 degrees is going to be 1/2, and time is 10 seconds. So that's I. And then we have initial value, or initial velocity 500. Sine of 60 degrees is going to be √3/2. So times, and that's times t. I need to put in 10. Okay. Minus 1/2 g is going to be, and actually the negative is already accounted for in here, so you just do 9.8. And then 10 seconds squared, and that's in the j direction. All right, so 500 times 10 is 5,000 times 1/2 is 2,500 I. And 5,000 over 2 is 2,500 √3 minus 100 times 1/2 is 50 times 9.8 is 490. And that is the j component. Okay, so that's roughly 2,500 I. Keep putting j for I. And the other is, if you put it in the calculator, 3,840 j. And so what this means is 10 seconds later, this projectile is 2,500 meters downrange of the initial launch point, and it is 3,840 meters high off the ground altitude. All right, so that's what this looks like. Now I am going to ask you to take a look at page 751 for shortcuts and formulas. They derive formulas for shortcuts to figure out the maximum height, which is of course the y-coordinate of the vertex, the flight time, the range. If you remember your quadratics really well, you don't need shortcuts for these. You know how to do it. But example 5 is taking into account a gust of wind, a reality factor that the formulas don't account for. So I want to make sure you read that problem and notice the adjustment that they do for a wind gust. They give the direction of the wind gust. Fortunately, it's a horizontal one that's pretty easy to figure in there. But that's the beginning of you doing problems where other factors are being allowed to affect the motion of the ball other than just the initial launch and then gravity. All right, thanks for listening.